going to talk about rational, irrational numbers. We're going to start just with the recurring decimals to get familiar with what are the recurring decimals, and then later on we're going to talk about rational, irrational numbers deeply. So the recurring decimals contain the digits that are repeated over and over again. For example, 0.222, 2.43, 53, and 0.14, 142, 142, and so on. So those are all the examples for the recurring decimals. Dots, we basically use the dots to show how the decimals recurring. For example, instead of writing the long 0.22222, we are writing 0.2 over the 2. We are writing a little dot to show that 2 in the recurring decimal, in the decimal occurs. Okay, so the same for 2.4, 35, where since, as you can see, the 35 recurs. To show this in a short way, we write 2.435, where we're going to put the 2 dots on 35 that shows this 35 recurring. When it is the 3 digits recurring, as like 142, we put the dot on the first and on the last. Where we have the 4 digits recurring, so the same rule like we did the 3 digits, so we're going to put the dot on first one, which is 8, and on the last recurring one is going to be 9, because 8019 recurring. Okay, this is the short way to do this. So now we are going to learn changing recurring decimals to fraction. So changing recurring decimals to fraction isn't that the normal decimal numbers. You cannot write this as 7 out of 10. 7 out of 10 is 0.7, but this decimal over here, 0.7 recurring, is 0.77777. So changing into a fraction is a little different here. So I'm going to say let x equals to 0.777. Basically, we are taking 0.7 recurring as just the x. So this is going to be the fraction. We're looking for x. So it's equals to some fraction. So we're going to multiply both sides by 10. So remember, when the 1 digit's recurring, you're going to multiply it by 10. When the 2 digits recurring, you're going to multiply by 100. When the 3 digits recurring, you're going to multiply it by 1,000. So, and so on, 4, 10,000, and so on. So if I multiply both sides by 10, I'm going to have 10x equals to 0.77777 times 10 will be 7.777. And I'm going to write down x equals to 0.77 beneath this and subtract those. So it's going to be left hand side taking away left hand side, right hand side taking away right hand side. 10x minus x will be 9x, and 7.777 minus 0.777 going to give you just a 7. And then by dividing both sides 9, you're going to have x equals to 7 out of 9. So if you just take your calculator and check, you will see actually 0.7 out of 9 equals to 0.7777 recurring. So this is the process how we change recurring decimals into a fraction. Let's do one more with the 2 digits. As we just said, if it is 2 digits, we're going to multiply by 100. So we're just going to say let x equals to 47. So you're going to multiply by 100. It's going to be 100x equals to 47.47. So write x beneath under that, which is the x equals to 0.47, and going to minus this is going to give you 99 x equals to, so right hand side 47.47 minus 0.47, taking away, so it's going to give you 47. So dividing both sides by 99 going to give you 47 out of 99, where we're going to write 0.47 recurring is equals to 47 out of 99. Let's do one more with the 3 digits number. So 0.125 obviously recurring. Let's say x equals 0.125, and 125. So 3 digits means multiply by 1,000. You're going to multiply it by 1,000. And we're going to have 125, 125. Subtract the x, we are going to have 999, x equals 125. So we're going to divide by both sides by 999. It's going to give us 125 equals to 999, where 0.125 recurring is equals to 125 out of 999 as a recurring. Okay, so let's do a little different problem. So this time 2 digits recurring, but we have a 9 in front, so it's going to be different, a little different. So first, like we just used to do, it's going to write x equals to 0.94774747, and then we are going to multiply by 100 as 2 digits recurring. Okay, so that's going to give you 100x equals to 94, 74, 74, 74. I'm going to then subtract. I'm going to write beneath under this, subtract the equations, and I'm going to have a 99x equals to 93.8. So I'm going to divide both sides by 99, and I'm going to just multiply both numerator and denominator by 10, and that's going to give me 908.38 over 990. So where I'm going to simplify this further, I'm going to have 469 over 495. So that means 0.947 recurring is going to be 469 over 495. Okay, so the set of real numbers can be divided into two sets as rational numbers and the irrational numbers. Here is the main topic here we are going to talk about. So rational numbers, the any number, if you can show any number in the form of fraction as a over b, we call this a rational number. But the irrational number is going to be opposite to the rational, which is cannot be shown as a over b. So example for rational numbers, I can say all fractions, because all fractions is already in a fraction form. We said if we can show it as a fraction, that means it's rational. If we cannot, it's irrational. So all fractions, obviously, all integers, because you can write all integers as like over 1, like just a fraction. For 8 is rational because you can write 8 out of 1. All mixed numbers, obviously, they are also a fraction. All terminating decimals. So the decimals like 0.23. It's going to be 23 out of 100. You can show it as a fraction, so it is what we actually wanted, rational. All recurring decimals as well, because we can show recurring decimals, this we covered, this we learned, as a fraction. And some squares, not all, some squares, so those are we call the perfect squares, that for example square root of 64, 25, those are giving us a perfect answer where we can write them as a fraction. And some cubes, which we're going to call them also perfect cubes with negative 8 or 64 also. 125 for example, cube root of, all of those are going to be irrational numbers. So when it comes to irrational numbers are pi. So we said we cannot show it as a fraction. As you know, pi is not a recurring decimal and it goes to infinity. So we don't have a way to show it as a fraction. So some squares, so those are we are going to call not a perfect squares, not a perfect cubes, like square root of 3, cube root of 5, and we have tons of examples there we can just refer to. Some trig ratios, okay, sine 20, for example, sine 50, sine 25, sine 1 degrees, for example. 1 degree can be shown as irrational, but some trigonometric functions ratios we are saying here, because sine 30 is not irrational number, because sine 30 is 1/2. So that's it, basically irrational numbers. The numbers that we cannot show as a fraction, we call it irrational. Numbers that can be shown as a fraction, it's called rational number. So let's, for example, work out this exercise. Okay, which of the following of these numbers are irrational numbers? So we're looking for irrational. Irrationals are that we cannot show as a fraction. So 2.5 not going to be irrational, obviously, because 2.1 is going to be 21 out of 10 or 21 out of 10, just a mixed number or improper fraction. It's not. Cosine 40, yes, it is going to be irrational number. And square root of 33, also irrational number, as it's not a perfect square. Mixed number, it's rational. Recurring, it's rational. Sine 30 is also rational. If you just plug this into your calculator, you're gonna see this is going to give you 1/2, a perfect answer, but it's not going to be true for cosine 40. And pi is also irrational. So we have here 1, 2, and 3 irrational numbers. So answer going to be cosine 40, square root of 33, and the pi. So, and we have also exercises, like they are giving us some like sort of set, and we need to select the numbers right in the correct sets. So we do know now rational numbers are numbers that we can show as a fraction. Integers are the whole numbers. So 4 out of 9 going to be rational number. It's not going to be integer, obviously. 4 out of 9 is a fraction, and that's the definition for the rational number. Any number can be shown as a fraction, is a rational number. I'm going to go over here. Square root of 36 is rational as well as integer, because it's a perfect square, it's 6. Square root of 2 out of 3 is going to be irrational. It's neither integer nor rational, because it's not a perfect square. Neither 2 nor 3 are a perfect square, so we're gonna just write it outside the set. Like this is a universal set, and we have irrational number set and integer set, so it's going to be outside of the rational integers. Square root of 4 out of 9 is going to be rational, because it's going to be 2 out of 3, because both 4 and 9 are perfect squares, and 4.9 obviously going to be rational, because we can show as 49 out of 10, and the pi going to be irrational, which is going to be outside of the rational integer set. So here we just done. If we know the definition well, this topic going to be super easy for all of us. So let's solve a few exercises. It says if x irrational for this triangle, is x rational irrational? So to find out this, if it is whether it's rational, we're going to use Pythagorean, where we're going to say x squared, the square of the hypotenuse, sum of the square of the legs. So we're going to find x squared equals to 100 plus 576, and then x squared equals to 676. So we're going to take the square root. We're going to have x equals to 26. So 26 is going to be rational number, as you can show it as 26 out of 1. So that means x going to be rational. Let's check one more, whether x is rational or irrational. The same strategy, we're going to use Pythagorean. X squared plus 4 squared equals to 12 squared. So we're going to have x squared plus 16 equals to 144, minus 16 from both sides, x squared equals to 128. So we're going to say x equals to 1.317085, ... means like this is not the all. So there is no recurring decimals here, so you cannot obviously show this as a fraction, as it goes to infinity. So we're going to say it's going to be irrational. So that's the end of rational, irrational numbers, also recurring decimals.